Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 14th, 2026, just yesterday. It introduces a new framework that matches the accuracy of computationally heavy methods like Monte Carlo tree search, but remarkably, it does so using about 1,000 times fewer tokens. The paper is titled MAXS Meta-Adaptive Exploration with LLM Agents, and as we'll see later, the implications for running complex agents efficiently are quite significant. So, Figure 1 illustrates exactly how these agents operate in practice. It presents a physics problem where a ball is dropped from a building and the agent must calculate its impact speed. Instead of just guessing, the agent dynamically leverages tools to fill in missing information. In the yellow section, it runs a search query to find the local gravitational acceleration in London. Then, moving to the right, it uses a code interpreter to perform the precise square root calculation, which ensures the final result is numerically accurate. Well, Figure 2 compares these different reasoning strategies side by side. On the far left, chain of thought simply moves in a single straight line from question to answer. In the middle, tree of thought and Monte Carlo tree search explore multiple branching paths, with the green panel highlighting how MCTS runs expensive simulations for every step. Then, the pink panel illustrates the new MAXS framework, which uses a reward-driven lookahead to pick the best path without simulating everything. The bar charts on the far right show the payoff, where MAXS consistently achieves the highest accuracy across benchmarks like MathVista and EMA. Alright, Figure 3 breaks down the architecture in detail. The left panel shows the standard loop where an agent receives input and calls tools like code or search. The right side reveals the meta-adaptive process. At the top, under Rollout and Lookahead, the system simulates multiple future paths, represented by the parallel columns, to test different tool choices. Moving down to the value estimation section, it scores these paths using three metrics, an advantage score for progress, plus variance and slope measures to ensure stability. Finally, the integration section at the bottom selects the optimal step, marked by the green bars, while the red stop button indicates the convergence mechanism that halts processing early to save compute. So, having seen the architecture, Table 1 now proves it works across 5 major benchmarks, including MathVista and Theorem QA. The table is split into 2 sections for different base models, with the top block focusing on the MIMO versus L7B model. Looking at the gray highlighted row, MAXS achieves the highest average accuracy of roughly 63%, clearly beating baselines like chain of thought and tree of thoughts. But the real story is in the far right column, which tracks token consumption. While Monte Carlo tree search skyrockets to nearly 10 to the power of 10 tokens, MAXS stays around 10 to the power of 8, delivering superior performance with about 100 times less compute. So, Table 1 established the performance. Now Table 3 breaks down why it works through an ablation study. Here, the authors systematically remove components one by one to measure their impact. Focusing on the top section for the MIMO model, the second row, labeled without Lookahead, reveals the critical finding. Removing this planning capability causes average accuracy to drop from 63% to 58%. This proves that simulating future steps is the primary driver of success. Meanwhile, the bottom row shows that removing trajectory convergence, or TC, barely affects the score, confirming it safely saves compute. Okay. While the previous table validated the components, Figure 4 now visualizes the overall inference timescaling laws, plotting accuracy against token usage. The pink line represents MAXS, and its steep trajectory places it in the most efficient region of the chart. The horizontal blue dashed line highlights a massive disparity. To match the accuracy MAXS achieves with limited compute, the Monte Carlo tree search method on the far right consumes nearly 1,000 times more tokens. Meanwhile, the vertical red dashed line indicates that at equivalent token budgets, MAXS leads the phi decoding baseline by approximately 8 percentage points. Wrapping up, 2 takeaways stand out. First, MAXS successfully bridges the gap between simple reasoning and expensive global search. Second, it does this while cutting token usage by a factor of 1,000 compared to Monte Carlo tree search. This efficiency opens the door for deploying much smarter agents at scale. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.